Good morning, sir. My name is Per Lakshman from Triple E Department. My roll number is 20955A0212. Today my subject is HVDC transmission lines. Today my topic is about HVDC transmission line using line commutated converter. An HVDC converter electric power from high voltage alternating current AC to DC direct voltage high voltage DC current HVDC or vice versa. HVDC is used as an alternative to AC for transmitting electrical energy over long distance or between AC power systems of different frequencies. HVDC's converters are capable of converting up to 2 gigawatts and with the voltage ratings of up to 900 kilowatts have, have been built, and even higher ratings are technically feasible. A complete converter station may contain several such as converters in series or parallel to achieve the total system DC voltage rating of up to 11 1100 kV. Almost all HVDC converters are inherently a bilateral network that converts either AC to DC or DC to AC inversion process. The complete HVDC system always includes at least one converter operating as a rectifier AC to DC, at least operating as a converter DC to AC. Some HVDC systems takes full advantage for this bilateral property. For example, those designed for the cross border of power trending others, and for example this designed to export for the power from a remote power system. It may be optimized for power flow in only one preferred direction. In such schemes, power flow is in non-preferred directions may reduce capacity or poor efficiency. An HVDC transmission line using line are becoming a more and more common in modern power systems. These chapters include the line commutator converters such as LCC, HVDC transmission line systems, and discuss the AC and DC protection schemes for the. It focus on the two terminals line commutating current source HVDC system consisting of two converter stations. One converter to operate as a rectifier, another one operating as an inverter connected by the DC transmission line. A general description of a converter station design is described to provide an understanding of a types of devices necessary to control and protect DC line and the terminal equipment. The psychology of the DC HVDC protection is similar to that for AC system protection. A grid bus will be normally be used to tied for the supply breakers to convert the transformer. The converter values are solid state thyristor walls in all modern converters design. The system, the protective system for the DC harmonics protection is the converter. And this is the circuit diagram for the line commutating converter. This is given to the three-phase high voltage AC supply, and it is converted to HVDC, high voltage DC current. And the line commuters is the in this we are telling about the basic line commutator 6 pulse bridge. The basic LCC configuration of HVDC uses a 3 pulse gigahertz bridge rectifier or 6 pulse bridge containing 6 electronic switches, each containing one of the three phases to one of the two DC terminal. As complete switch element is usually referred to as a valve and irrespective of the constructions. Normally two valves in the bridge are connecting in any time. One of one to a phase on the top row and another one is a different row on the bottom row. That the two conducting walls connected to of the three AC voltages in the AC series and DC terminals. Thus the DC output voltage at the given instant is given by the series combination of two AC voltages. And because of the unvalidable inductance in the AC supply, the transition of the one pair of conducting walls or to the next does not happen instantly. Rather than this is short overlapping period, two will when two walls on the same row of the bridge are conducting instantaneously. For example, in if wall 1 V1 and V2 are the initially conducting and then wall 3 wheels is turned on, the conduction passes from V1 to V3. But the shorter period, the both of the both of our valves are conducts instantaneously. During this period, DC output is given by the average of voltage of phase 1 and phase 2 and minus that voltage phases is 3. The overlap angle is mu in the HVDC converter increases the with the old load current, but it is typically around 20 degrees at the full load. And this is a circuit diagram for line commutating converter and HVDC line. We are giving the three phase AC supply and we have connected the three inductors and we have used the thyristor for the to operate the DC commutator. And when V1 and V2 are conducting, then UDN will be equals to UNL1 by minus UNL3, and this is the supply of line 1 and line 3 which is conducts by the circuit, and the output voltage is VD. We are giving the in second circuit we are giving the circuit UL1 N1 and UN2 and L3, that is LC, and we have three inductors. The circuit diagram is when V2 is conducting, V1 is commutated to V3, UD and half into the formula for output voltage is equals to UD is equals to 1 by 2 UL11 plus UL1N2 minus third UL13, and this is the waveform for the circuit line commutating current in currents in each valve. We are giving that each pulse and either 6 pulse DC voltage are line to actual voltage. DC voltage and line to line voltage are the fluctuating voltages, and the output voltage of VDC is equals to V average, and this is a 3 into root line peak value by pi cos phi minus 6 frequency into LC into ID. The the value of VLL peak, that's the peak value of the current to line input voltage. Then on the one converter of the converter transformer, angle alpha is the angle firing angle of the thyristor, and LC is the commutating inductance per phase, and ID is the direct current. When we are giving the IV voltage, the voltage is given to the circuit, the output is U. The firing angle alpha represents the time delay for the pointing at which the voltage across the wall becomes positive, at which point of diode will start to conduct and thyristor will be turned on. From the foregoing education, it is clear that as the fire angle increases, then that means DC output voltage decreases. It is inverse, alpha is inversely proportional to voltage. In fact, with a line commutator converter, the firing angle represents the only fast way of controlling the converter. Firing angle control is used to regulate the DC voltage of both ends of the HVDC system continuously. In order to obtain the desired level of power transfer, the valve voltage and current for the inverter operating with delta is equals to 20 degrees and mu is equals to 20 degrees. And the DC output voltage of converter steadily becomes less positive as the firing angle is increased. Fire angle increases up to 90 degrees, corresponding to rectification, and the results in positive DC voltage. While firing angle is above 90 corresponding to inversion, that goes to inversion process, the result is negative DC voltage. However, the firing angle can't be extended all the way to 180 degrees for the two reasons. First, the allowance must be made for the overlap angle mu, And the secondly addition extension angle beta, which is needed for the wall recording beta with the angle. This is the topic about. Thank you, sir.